So today we're going to talk about velocity and then other rates of change. And this is the first day of it. And this is going to sound very, very much like your physics class, okay? So just telling you, because we're talking about position, displacement, velocity, acceleration, all those things you either learned last year or you're currently learning in physics, okay? So position, okay? So position, a lot of times we'll use the function notation S of t, okay? That's if we're moving in a straight line. For Calc AB, we have to be moving in a straight line, like left, right, up, or down, okay? But if you're not determining whether you're going left and right or up or down, we use S of t for position, okay? If we're going left and right, then we reserve that for X of t, okay? So we use X of t for position like that, okay? And so this is for a particle moving on the x-axis. So if we're going up and down, then the notation we would use for the position at a given time would be y of t. And we use that for a particle. A particle just represents some like point moving or something moving, okay? So moving on y-axis. All right, so the definition of what displacement is its change in position. Okay, so we could use the delta S, the change in the S position. Okay, so that would be S of T sub final minus S of T sub. You can use initial, or some people use original, okay? If we're talking about on the x-axis, then it would be delta X, and it would be X of T sub F minus X of T sub I. If it was moving on the y-axis, it'd be delta Y, and that'd be Y of T sub final, okay, and then minus Y of T sub I. Okay, so those all represent displacement. Displacement is going to be a distance unit, so it's going to be like meters or yards or feet or miles, okay? And then average velocity, okay, velocity is always going to be a distance unit over a time unit, okay? So the definition of what average velocity is it's the displacement over the time unit, okay, or over delta t. So a lot of times it's delta x over delta t. And so it would be x of t sub final minus x of the initial time. A lot of times the initial time is 0, okay, over t sub f minus t sub I. The final time minus the initial time, okay, or the starting time. This should look familiar. This is slope. This is average rate of change. Average rate of change is the generic form. Average velocity is a specific one. So average velocity, okay, or velocity is a rate, but it's a specific rate where you have a distance unit I cannot spell, sorry, over a time unit. So what you guys are familiar with is miles over hours, right? That'd be miles per hour. That's speed limits, right? Okay. All right, so now let's move on to the next thing, which is instantaneous velocity. So instantaneous velocity, which you'll also hear being called just velocity, is we use the symbol v of t, and it's the derivative of the position function. So s prime of t, or it could be x prime of t, or it could even be y prime of t. these are all position functions. So if you take the derivative of it, you get the velocity. And okay, you guys couldn't do this last year, okay, in physics, because you need calculus, all right? You can give me the velocity at one moment in time. Any moment in time, you can give me the velocity, okay? The acceleration, all right, a of t, is simply equal to the derivative of the velocity. So v prime of t. Or you could also do the second derivative of position, which would be s double prime of t or x double prime of t, now that we know higher order derivatives, or y double prime of t. Okay? Now, I want to talk about the units for acceleration, okay? So it's the change in velocity over the change in time, the instantaneous change in velocity over the instantaneous change in time, okay? So units for velocity are something like this, meters per second over, and then the time unit would be seconds, okay? So we get, this is meters per second, or another way of simplifying this that you're going to see is, this is a complex fraction, so you can multiply by seconds over seconds. And so another way to explain acceleration is this could be meters per second squared. So you can either write acceleration as meters per second, or meters per second squared. They're the same thing, okay? I just wanted to let you know on that. All right, so now this is really the next part of the lesson is really for people who have not had physics or you really didn't have a solid grasp on physics, okay? What's funny is I just did this like the same lesson just 2 days ago with my physics class, okay? So we need to look at, okay, velocity, what is velocity or what is acceleration due to velocity, okay? So this is kind of the key to it. It adds meters per second every second, okay? So we're gonna take a look at that and talk about, okay, what does that cause? And that's next. So a velocity of, let's say we start out with a velocity of 10 meters per second. And let's have an acceleration of 2 meters per second. So what that means, every second, this velocity is going to go up 2 meters per second. So every second, going to go up by 2 meters per second. So this could also be written as 2 meters per second squared, okay? They're interchangeable. So at time 0, we already know the velocity is 10 meters per second, okay? 1 second later, the acceleration, because it's 2 meters per second, 1 second later, that's going to cause this 10 meters per second to go 10 meters per second to go up by 2. So now this would be 12 meters per second. 1 second later, 14 meters per second. 1 second later, 16 meters per second. 4 seconds later, we're at 18 meters per second. 5 seconds later, we're at 20 meters per second. 1 second later, we're going to be at 22 meters per second. 1 second later, we're going to be at 24 meters per second. 1 second later, we're going to be at 26 meters per second. And 1 second later, we'll be at 28 meters per second. Okay? And so I want you to look at this. Okay, so we had a positive velocity and we had a positive acceleration. So it was adding on more and more and more every second, more velocity to the prior velocity, right? And so what happens here, I'm trying to find my pin, is that this has caused it to go from 10 to 12. It's speeding up, okay? So this whole time, it was speeding up. All right, so let's look at a different scenario. We're gonna look at combinations of signs, okay, of velocity and acceleration. So now I wanna look at, let's put in, let's do 10 meters per second. But this time, let's have an acceleration that's -2 meters per second, or that'd be equivalent to -2 meters per second squared. So once again, at time 0, we're going to be at 10 meters per second. But what this is going to do is it's going to remove velocity each second. So it's going to remove 2 meters per second every second. So 1 second later, we're going to remove 2 from the 10, and that would make us 8 meters per second. 1 second later, we'd be at 6 meters per second. 1 second later, we'd be at 4 meters per second. 1 second later, we'd be at 2 meters per second. 1 second later, we'd be at 0 meters per second. And what that means, if you're going 0 meters per second, that means you have stopped. So whenever you hit 0 meters per second, this means you've stopped. Okay, now before I fill in the rest of the table, okay, I want to talk about what just happened. We started with a positive velocity and we had a negative acceleration, which caused us to remove velocity from positive velocity, right? And what that caused is this to get smaller and smaller and smaller. So what's happening here, if we go from 10 meters per second to 8 meters per second to 6 meters per second to 4, we are slowing down. Okay, you can see that in the velocities. So this is causing us to slow down, or slowing down. I should say slowing down. All right, so now we hit 0, okay? And now 1 second later, now we're at -2 meters per second. Because remember, it keeps removing it, okay? So every time it keeps removing. And now 1 second later, we're going to remove 2 from -2, which actually makes it become -4 meters per second. And 1 second later, we're now at -6 meters per second because we've removed it, right? And at 9 seconds, okay, or 1 second later, we'd be at -8 meters per second. So after we stopped, what happened here is we were starting to speed up. Now, why were we speeding up? Okay, because after the 0 meters per second, we went into negative velocity. And now when you start removing something from a negative value actually makes it bigger negative, right? So so you see, we're going from 2 to 4 to 6 to 8. This is speeding up, but in a certain direction, okay? And I should have said this earlier, okay? Positive velocity, those of you who didn't have physics, positive velocity means you're moving in the positive direction. So like if you're on the x-axis, you're moving to the right because that's the positive direction. This negative means you're moving to the left or in the negative direction, okay? So this is slowing, or not, sorry, right here, this was speeding up. Okay, because all of a sudden now the velocity became negative and we're removing negative, but it's actually adding more negative, right? Okay. So now let's go to a negative velocity. So -10 meters per second. And let's have a positive acceleration. So 2 meters per second, which could be written as 2 meters per second squared. So at time 0, we're at -10 meters per second. Okay, so this is positive. The acceleration is positive, so that's going to add every second. It's going to add 2 meters per second. So 1 second later, we're at -8 meters per second. 1 second later, we're at -6 meters per second. 1 second later, we're at -4 meters per second. 1 second later, we're at -2 meters per second. 1 second later, we're at 0 meters per second. And that's telling us we have stopped because the velocity hit 0. And if you take a look at our velocities, we went from -10, -8, -6, -4, -2. We are now slowing down. All right. And so over here, 1 second later, okay, now remember we're adding, right? So we now are 2 meters per second. 1 second later, we're at 4 meters per second. 1 second later, we're at 6 meters per second. And then 1 second later, we're at 8 meters per second. And what happened? We are now speeding up again, right? Okay, so why were we speeding up? Here's why. The velocity, after we hit 0, the velocity became positive, and the acceleration is positive. So if the velocity is positive, we're adding velocity to an already positive value. So it's just going to get more positive, right? It's going to get bigger in a positive way. Okay, so that's what's happening here. Okay, and so that's why we're speeding up. All right, last one. Okay, velocity is negative 10 meters per second. The acceleration is negative 2 meters per second, or negative 2 meters per second squared. At time 0, we're at negative 10 meters per second. 1 second later, we're at negative 12 meters per second. 1 second later, we're at negative 14 meters per second. Because we have a negative velocity and we're adding, or we're removing 2 meters per second, right? Each second, okay? But when you have a negative value and you're removing, right, you just become more negative, right? You get more in debt, okay? So at 3 seconds, we're going to be at negative 16 meters per second. At 4 seconds, negative 18 meters per second. At 5 seconds, negative 20 meters per second. 6 seconds, negative 22 meters per second. 7 seconds, negative 24 meters per second. 8 seconds, negative 26 meters per second. And at 1 second later, it's going to be negative 28 meters per second. Okay, and so we were speeding up the entire time, okay? Okay, so I always do this every year. What's causing us to speed up and what's causing us to slow down? So if you have an understanding of this, okay, you can tell me why we're speeding up or why we're slowing down, okay? So I should say this, speeding up is equivalent to, say, speed is increasing. Okay, and slowing down I slide that up. Sorry. Speeding up is equivalent to speeding up is equivalent to speed is increasing, and slowing down is equivalent, okay, to speed is decreasing. So sometimes on the AP exam, they ask for where is the speed increasing? Where is the speed decreasing? Well, they're talking about speeding up and slowing down when they say that, okay? I'm going to zoom out a little bit because I kind of need to refer back to these tables, okay? All right, so how do you know when you're speeding up and when you're slowing down? Okay, so we were speeding up the entire time here, but we were also speeding up the entire time here. So that's one of the giveaways is how do you know when we're speeding up? And if you're in class, I'd ask you and try to draw it out of you, but I'm just gonna have to tell you. Okay, so here we go. How do you know? It's when the velocity and acceleration are the same sign, okay? So we know, this is an important thing, okay? The particle is speeding up when the velocity and acceleration are the same sign. So how do we know when it's slowing down? Okay, so we're slowing down when they're opposite signs, Because if you're positive velocity and a negative acceleration, look what happened, okay? You're canceling, by that being negative, you're canceling out some of this positive velocity, right? And so it starts to slow down. Same thing if you have a negative velocity and a positive acceleration. You're canceling out some of those negatives, right? Each time you're canceling out 2 of those negative meters per second, okay? So the particle is slowing down when the velocity and acceleration are opposite signs. Okay, a few more things that you need to know, okay? When you have positive velocity, that means you're moving to the right or you're moving up. So I'm going to slide this up a little bit, okay? So all of these are going to be important, okay? Particle is moving right / up when v of t is positive or greater than 0. Okay? Particle is moving left or down when v of t, the velocity, is less than 0. Okay? And then we know the particle is stopped when v of t equals 0. When the velocity equals 0. And then 2 more things, okay? How do we know when it changes directions? So how do we know when it changes from going right to left, okay? Or from going up to going down? Well, we know when it's going up or right, it's positive, right? And we know when it's going left. So it would have to change signs, okay? And so that's the idea of how do you tell when a particle changes directions? It's when velocity changes signs, okay? So particle changes directions when v of t changes signs. Okay, and then the last thing is, how do you figure out speed? How do you calculate speed? What is speed? Well, speed happens to be this, okay? So speed is simply the velocity without the sign, okay? So how do you make something become positive? You take the absolute value of it. So speed is defined as the absolute value of v of t. All right, so that's a lot of the physics that you're going to need to know to be able to do the calculus that we're talking about, okay? All right, so now let's look at some graphs next. So this is a position graph, okay? And a position graph tells us the position for any given time. So the horizontal axis is time, and we're going to measure that in seconds. And then this position function, S of t, is going to be measured in, let's say, meters. Okay, so if we take the slope of any of these segments that you see, because this is made up of piecewise linear function, right? A bunch of pieces. If we find the slope, that'd be the change in y over the change in x. So that the units would be meters over seconds, okay? So we can get the velocity, okay, graph by finding the slope of each of these segments and graphing that slope. So from 0 to 1, the slope is always the same. From 1 to 4, slope is always the same. From 4 to 6, the slope is always the same. So when we graph this, it's going to wind up being little horizontal lines, okay? And then from 6 to 8, slope's always going to be the same, right? Okay, so the velocity is always going to be the same on this time interval. The velocity is always going to be the same for this time interval. And then same thing for this one, and then same thing for this one, okay? So the velocity, this is going to be measured in meters per second. And the time is also measured in seconds, okay? So the slope for this one, okay, we're going up 2 and over 1, right? So the slope would be 2 for this, which means my velocity would be 2. And get my handy dandy ruler. And between 0 and 1, I'm going to graph the horizontal line 2 because the slope is always 2 in this interval. So I'm going to go from here. I'm just going to graph this right here. Now, there's a derivative on this side, but there won't be on this side because there's a corner right here, okay? So this is going to be a closed dot. It's only a one-sided derivative, and it would be the right-hand derivative. And this is going to be an open dot. Okay, so then this next segment goes from 1 to 4, right? And we go up 1 and over 3. So that would be a slope of 1/3. So that would start like somewhere right about here. And at 4 seconds, it would end up right about here. And so I'm going to draw a horizontal line there. And once again, there's a corner here. So this side's going to be open because we can't take the derivative. And right here, it's also a corner. So that one's going to be open. All right. And then this one, we went from 3 all the way down to -3. So that's a decrease of 6. But we did it in a horizontal distance of 2, right? So we went down 6 meters. So that'd be -6 meters over 2 seconds. So that'd be -3 for the slope. Okay. So we're going to be -3 meters per second from 4 to 6 seconds. So that would look like this. Okay. And remember, slope is derivatives, right? So these are all derivatives of these, right? Okay. Or velocity is a derivative of position. Okay. So then from 6 to 8, okay, we were at -3, now we're at 1. That's an increase of 4, but we did it in 2 seconds, right? So my slope would actually be 2 meters per second. So I'm going to graph 2 from 6 to 8. So I'm going to graph 2 from 6 to 8. I just put 2 little dots to help me line it up quickly with my ruler. Okay, and once again, this is a corner right here, so I can't take the derivative here. And there's only one side here, so I can take the derivative, and so it'd be a left-hand derivative. And so I'm going to put a closed dot there because that would be the derivative right there. Okay, and this is a graph of the velocity. It's also a graph of the derivative, right? That's exactly what it is, okay? So because the derivative of position gives you velocity, this is the derivative graph for this, okay? For this function, okay? And we've already done that, right? Okay, let's go to the next thing where we're reading stuff off of a velocity graph. All right, so now I'm going to give you a lot more information, okay? Or we're going to pull a lot of information off of this, okay? So one of the, I'm going to ask you a lot of questions too. So one of the questions is, this is the velocity, okay? So this is measured in seconds, okay? And this is going to be meters per second. Okay, so the question is this: when did the particles stop? Okay, so how do we know when it stopped? Well, we know it stopped when the velocity is 0. Is the velocity ever 0? Yeah, it is. At time 0, the velocity was 0 because this is anytime it touches the x-axis, the velocity is 0. So the velocity is 0 here, its velocity is 0 here, and also the velocity is 0 at 10. Okay, so the particle is stopped at t equals 0 seconds, t equals 4 seconds, and t equals 10 seconds. And you got to give me a reason why. Okay. So yeah, did you just guess, or how do you know that? Okay. So you got to prove to me, you have to justify why you're saying this. Okay. And so here's why. Okay. It's because v of t, which represents the velocity, is equal to 0 at t equals 0, t equals 4, and t equals 10 seconds. Okay. Now I'm going to give you an alternative way of saying this, because there is another way of saying it. Instead of saying because v of t is equal to 0 at t equals 0, t equals 4, and t equals 10, you could also say it this way: because v of 0 equals 0, comma, v of 4 equals 0, and v of 10 equals 0. Okay, so you could say it that way too, and that would be equivalent to because v of t equals 0 at these particular values. Okay. All right, the other question I want to ask you is this: where did it change directions, or did it change directions? So how do we know when it changed directions? Well, we have to look at the velocity, right? And we know what direction it's moving by the sign of it. So if the velocity changed from like being positive to negative, that would mean it changed directions, or from negative to positive. Well, does that happen anywhere on this graph? And it does. And it happens right here at 4 seconds, because just before 4 seconds, the velocity is positive. How do I know that? It's above the x-axis. Okay, and just right after 4, the velocity is negative. How do I know that? It's the velocity, or the graph is below the x-axis. Okay, so the particle changed directions at t equals 4 because, and you would say because v of t changes, or changed, I should say changed, from positive to negative. And if you put a period right here, you'd be wrong. Okay, because it's not that it changed, it's not just that it changed signs from positive to negative. We know it changed directions at t equals 4 because it changed from positive to negative at t equals 4. So you gotta throw that in, at t equals 4. Okay, so don't forget that the at part, at t equals 4. It's doing this at that t value. That's why we know it changed directions at t equals 4. Okay. All right. So now we're going to talk about speeding up and slowing down. Okay. So we got to look at this velocity graph, but the derivative of velocity is acceleration. Okay. And derivatives are slopes. So right here from 0 to 2, because it's above, I know my velocity is positive, and I know my slopes on this segment are all positive. So right here, I know velocity and acceleration are both positive. So right here, from right here to right here, okay, I know v of t is greater than 0. You know, I'm going to get a smaller pen. And I also know a of t is greater than 0. Okay. Again, why velocity is greater than 0? Because it's above the horizontal axis. Why is acceleration positive? Because this line segment is going up and the slope is positive. Okay. Now, we can talk about the acceleration here, because the acceleration is the same the whole entire time. Okay. It's going to be negative because this slope is decreasing, but the velocity changed. So I'm not going to do this whole segment. I'm going to go from 2 to 4. Okay. So I'm going to describe 2 to 4. So from 2 to 4, because the graph is above the horizontal axis, I know my velocity is positive. So v of t is greater than 0. I know the slope here is negative, so I know a of t is less than 0. And then let's take a look from 4 to 6. Okay, so now my velocity is now negative because it's below. So that's another section I'm going to talk about. Okay, so here I know v of t is less than 0 because it's below. I know the slope is negative here, so a of t is less than 0. And then from 6 to 8 here, okay, I know my velocity, okay, is negative because it's below the horizontal axis. So v of t is less than 0. And there's the slope here would actually be 0, okay? So a of t, the slope is actually equal to 0. So there's no acceleration, okay? So if there's no acceleration, you can't be speeding up or slowing down, right? Okay, so then from 8 to 10, okay, this piece of the graph is below, which tells me the velocity is negative. So v of t is less than 0. I know this segment right here has a positive slope, so a of t is greater than 0. And what this tells me is right here, and let me grab my other pen. Okay, so v of t is greater than 0 and a of t is greater than 0 from 0 to 2. That means we're speeding up. Right here, v of t is greater than 0, but a of t is less than 0. What does that mean? That means on that interval, we are slowing down. On this next interval, v of t is less than 0 and a of t is less than 0. Okay, they're both the same sign, so that means we're speeding up on that interval. Here, v of t is less than 0, but a of t is equal to 0, so we're not speeding up or slowing down, so I'm not going to say anything, okay? We're just staying the same velocity. And then from 8 to 10, okay, from 8 to 10, the velocity is negative and the acceleration is positive, so this means we are slowing down. Okay, now, speeding up and slowing down is based on either the velocity being positive or being negative. So it is not, okay, I'm going to say this, it is not speeding up or slowing down at 0, at 4, or at 10. Why? Because at those values, the velocity is not positive or negative. It's 0. Okay, so we cannot include those when we talk about speeding up. Okay, so we can't include 0 and we can't include 4 if we're talking about speeding up and slowing down. Okay, similarly, this isn't going to happen yet. Okay, but you also can't include it if the acceleration is 0. Okay, so the acceleration and velocity either have to be both be positive or both be negative or opposite signs. Neither one could be 0. Okay, if either one is 0, we can't include that in our description of where it's speeding up and slowing down. Okay. All right. Next thing, what does a speed graph look like? Okay, so we just got done talking about this, and speed is equal to the absolute value of velocity. Okay, so what does the absolute value do? Well, if it's positive, it stays positive. But if it's negative, it becomes positive. All right, and v of t are the y's. So the y's, if the y's are positive, they stay positive. If the y's are negative, then when we take the absolute value of it, they become positive. So the only place the y's are negative is down here. And we did these graphs last year in Honors Math 3. Okay, so right here, this part of the graph is negative. So what's going to happen is this causes it to reflect over this horizontal axis. So this part stays put, but this part gets reflected over. So this part, instead of coming down, we're going to go up, okay? So this whole part stays the same. So let's start right here at 0, 0, and at 2, 4, and at 4, 0. Okay, so let me connect those so we can start with that. Okay, so that's this part of the speed graph. This part right here, well, it was at 6, -4. Now this point right here is going to become 6, 4. So that's going to be up here. So it's right here, still right here, but now it's going to come up this way. And then from 6 to 8, it stayed -4, but because we're taking the absolute value of it, it's going to become +4. Okay, and then we come up to 10, but in this case, we're going to have to go down to 10. I actually should say 10, 0, okay? And guys, that's the graph of speed, okay? So if this is the velocity graph, this is the speed graph, okay? That's going to be useful for some other things we do later on, okay? Just so I want to make sure you know that, all right? All right, and then the last thing we want to do is I'm going to have to zoom out a little bit, is I want to create the acceleration graph, okay? So if we have the velocity graph, all we have to do is take the derivative of velocity and graph the acceleration, okay? So because these are all line segments, our acceleration graph are going to be horizontal lines. So right here, okay, the slope, we go up 4 and over 2, so that'd be a slope of 2. So from 0 to 2, the acceleration would be 2. So I'm going to graph that. And so this left side is going to be a closed dot, and the right side is going to be open dot, because there's a corner right here, all right? And right here, there's only a right-hand derivative, and that's why we can take the derivative, and it's a closed dot. Okay, so this next segment, the slope, well, we went from 4 to -4, so that's a decrease of 8, but we did that in 4 seconds, right? So -8 over 4, okay, would give you -2. So we're going to be -2, the slope's -2 from 2 to 6. Okay, so once again, we are going to, sorry, I was interrupted there for a second. Somebody came in. So I lost where I'm at. Okay, so the slope is -2, and it's -2 from 2 to 6. Okay, so -2 from 2 to 6. We're going to draw that. And once again, at 2, corner, so open dot, and 6, corner, open dot here. Okay, and then from 6 to 8, okay, this slope would be 0, right? So from 6 to 8, how does that show up on the acceleration? That shows up, and it's going to be drawn right on the t-axis, right on the horizontal axis from 6 to 8. We're just going to draw right along here. Okay, and once again, a corner here and a corner here, so these are going to both be open. And then this slope here, okay, we're going to go up 4, but we're going to do that in 2 seconds, right? So 4 over 2 would be 2 again, right? And so it's going to be 2 from 8 to 10. Okay, so this is going to be an open dot right here because there's a corner there. And this is going to be a closed dot because it's only a one-handed derivative, and it'd be the left-hand derivative right there. Okay, and that is the derivative for this graph, okay? But it's for the derivative of velocity winds up being acceleration, okay? So now we're getting into problems that are more like what you're going to see for homework, okay? So that was just a lot of discussion and a lot of like explanation and how to read these graphs, okay? And what do the graphs tell us, all right? So the coordinates S of a moving body for various values of t are given, okay? So this is feet, so this is gonna be position, right? All right, and for a given time, like at the start, at 0 seconds, it's 3.5 feet away from where you're measuring. 1 second later, it's to the left, 8.5 feet, okay? And this would be to the right, okay? So I wanna estimate the velocity, okay? At 1.0, at 2.5, and 3.5. And I'm gonna do each of these a different way just to make you remember the different ways we can do estimate rates of change, okay? And so V of 1.0, okay, we can estimate, and I'm gonna do a right-handed derivative, okay? So, or not a right-hand derivative, sorry, a right difference quotient, okay? So what I'm gonna do is I'm gonna pick up this -10 right here. So that's -10 feet. And I'm gonna subtract, and if I wanna do a right, okay, I picked 1.5 because that's one value to the right, okay? And I wanna subtract the -8.5. So minus -8.5 feet all over 1.5 minus 1.0. 1.5 seconds minus 1.0 seconds. Okay, so that winds up being -10 feet plus 8.5 feet over 0.5 seconds. Okay, so then this is equal to, this would be -1.5. I forgot to put the t there. -1.5 feet over 0.5 seconds. And when we go to divide that, that would wind up giving us -3 feet per second. Okay, and this was a right difference quotient. Okay, so I'm going to do the same thing, but I'm going to do a left difference quotient for 2.5. So V of 2.5, we could estimate, okay? So 2.5, so I'm going to pick the one to the left of it, right, to use, okay? So this one's going to be -4 feet minus the -8.5 feet over 2.5 minus 2.0. So this would be -4 feet plus 8.5 feet over, and this becomes 0.5 seconds. And then this becomes 4.5 feet over 0.5 seconds. And when we go to divide that, we wind up with 9 feet per second. Okay, so now at 3.5, I want to do what's called a symmetric difference quotient. I should say this is a left difference quotient. Okay, and then V of 3.5 is equal to, and we're gonna use 3 and we're gonna use 4 because we're going equal distances either side of the 3.5. So it's gonna be 27.5 minus 3.5. And this is gonna be in feet. And I just put feet here because I forgot to put it on each one. That's the only reason, okay? And then 4.0 seconds minus 3.0 seconds. Okay, so when you subtract this, that would give you 24.0 feet over 1.0 seconds, which gives you 24 feet per second. And that's a symmetric difference quotient. Okay, so I'm not saying you have to do it all three ways. Okay, on the homework. I'm just saying, you know, I'm just refreshing your memory that there's three different ways you can estimate a derivative. Okay, so you can use a right difference quotient, a left difference quotient, or a symmetric difference quotient. What the one you'd want to pick is, and it doesn't matter because they're all 0.5 away here, but what you'd want to really do is pick the two that are closest to where you're trying to find it at. Okay, like if this side, let's say this is 1.5 and this is 0.8, you'd want to pick the 0.8 one. Why? Because they're closer. So you want to pick the two that are closest together to where you were trying to actually find it. Okay. All right. Okay, so let's go to the next thing. So this problem deals with the number of gallons of water in a tank T minutes after the tank has started to drain, and they're giving you a function that tells you the number of gallons. Okay, so this is not a rate. It's just how many gallons are in the tank at a given time after the drain has started, okay? So how fast is the water running out at the end of 8 minutes? Okay, so that's going to be a rate, right? How fast is it coming out? Not how much is in there, but how fast is it coming out? Okay, so we're gonna have to take a derivative on this. Okay, so I want you to understand that. Okay, this is the time, and it's going to be measured in minutes. Okay, and the vertical axis is this Q of T. It's the quantity, right? That's why they're using Q, and it's the number of gallons of water in the tank. Okay, so I'm going to turn this way. Okay, sorry, I have to write it this way. The number of gallons of water in the tank. Okay, and so this function gives you it's drawn out here, and you could figure out if we knew exactly what this looked like, and you could graph it in the graphing calculator, you would know that for a given time you could find how many gallons are in the tank. Okay, but the slope of that, and that's what's important here, is the slope. If we took the derivative, it would be gallons of water per minute. Okay, and that's what we're trying to figure out, is how fast is it coming out. So that'd be gallons per some rate of time, some time unit. Okay, all right, so Q of T is this, which means Q prime of T would equal, okay, so that's a constant, so that's going to be 0. And negative 12,000 T, well, that just becomes negative 12,000. And 150 T squared becomes plus 300 times T. All right, so this gives us the rate of change at any moment in time. Okay, so we want to do this at the end of 8 minutes, right? So that would be Q prime of 8. So that's negative 12,000 plus 300 times 8. So without a calculator, that would be negative 12,000 plus 2,400. And that gives you a value of negative 9,600 gallons per minute. Okay, so what does the negative mean? It means the number of gallons is decreasing 9,600 gallons per minute. Well, if it's decreasing that amount, then that's the rate at which it's coming out, right? That's how fast it's running out. Okay, so the water is running out of the tank at 9,600 gallons per minute. All right. Now, there's a different question that I could ask you on this, okay? And that is at what rate is the number of gallons of water in the tank changing, okay? And that would be a different answer than what we just wrote, okay? Slightly different, okay? We would say on that one, okay, so I'm just adding extra to this, okay? Because they always ask this on the AP exam, okay? The number of gallons of water in the tank is decreasing because that amount, because this rate is negative, the amount's got to be decreasing, okay? 9,600 gallons per minute, okay? And then we could say T equals 8 minutes. And I just realized I forgot to say this. Okay, so the water at the previous answer, okay, the water is running out of the tank at 9,600 gallons per minute at the end of 8 minutes. Okay, so if they ask you to interpret it, then this is what you'd say. The number of gallons of water in the tank is decreasing 9,600 gallons per minute at T equals 8 minutes. All right, and that'd be good. Okay, now there's a second question here, and that is this. What is the average rate at which the water flows out during the first 8 minutes? So during the first 8 minutes, that's an interval of time, not a moment in time. This one was a moment in time. That's one reason derivative. This is an interval of time, okay? And it's equivalent to saying average velocity, okay? But we want to find the first 8 minutes. So that's between 0 and 8 minutes. So what we have to do to answer this is we got to find Q of 8 minus Q of 0 over 8 minus 0. And in your calculator, you just put Q of 8 in, you put 8 in for Q, and it would give you 153,600, and that would be gallons, okay, minus the 240,000 gallons, and that's Q of 0. And divide that by 8 minutes, right? And this is gallons. And so that the top gives you negative 86,400 gallons per 8 minutes. And so if you divide that, you get negative 10,800 gallons per minute. Okay, so the average rate at which water flows out during, you could just rephrase this, during the first 8 minutes is negative 10,800 gallons per minute. Okay? And that's how you'd answer this question. And you have a similar question on your homework like this, okay? All right, let's go to the last problem. So for this last problem, a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, which is about 109 miles per hour. And it reaches a height, which is called S, And we can get the height that it reaches by knowing the time. So it's 160t minus 16t squared, and that's after t seconds. So you put a time in it, and it tells you your height, okay? So here's something that if you haven't had physics, you wouldn't necessarily know, okay? Even if you've had physics this year, I haven't talked about it yet, okay? But how high does the rock go, okay? So when the rock goes up, okay, once it reaches the top, it actually stops for a moment in time at the very top and then starts to fall and come back down. So when it reaches the top, the velocity is 0, okay? So when a rock or anything that gets thrown up, okay, thrown like a baseball or anything else, okay, when a rock is at its highest point, the velocity is 0, in this case 0 feet per second. Okay, so how can we get this? Okay, how can we figure this out? Well, if we can figure out all right, if we can figure out the velocity, okay, and set it equal to 0, and then solve for it, we'll have the time it reached its highest point, and then all we'd have to do is take that time and put it into this function and get the height out. Okay, so that's the idea behind it. So S of t is equal to 160t minus 16t squared. The derivative of this, which is S prime of t or V of t, would be equivalent to 160 minus 32t. If we set that equal to 0, 0 would equal 160 minus 32t, which means 32t would have to equal 160, which means t would have to equal 5. Now that is 5 seconds. Okay, so now we know it takes 5 seconds for it to reach its highest point. All right, so now what is that highest point? Well, because I have the time it reaches it, I can put it into this function. Okay, so S of 5, and I get 160 times 5 minus 16 times 5 squared, which winds up giving you 400 feet. Okay, so the rock goes up 400 feet. Up into the air, 400 feet. That's pretty high. Okay, if a story is 10 feet, okay, that's a 40-story building. Okay, all right, end with that question. Okay, let's go to the next one. So this time we need to find the velocity, okay, and we also want to find the speed of the rock when it is 256 feet above the ground on the way up and also on the way down. Now it reached 400 from above, right? It reached, I should slide this down a little bit. Maybe I do need, hold on, let me zoom out a little bit. Okay, so from up here, okay, we have the position and we have the velocity, okay? So we want to know the time in which the position is 256 feet. Now, it hits 256 feet on the way up to 400, but then also on the way back down from 400, right? It's going to hit this 256 feet. So this is going to hit it at 2 different times. And then we'll figure out those times and then put those into the velocity, and we'll have the velocity. And once we have the velocity, we can get the speed, okay? All right, so we want this position to be 256 feet. So 256 is equal to 160t minus 16t squared. I'm going to move, because since this is negative 16t squared, I'm going to move this over to the left-hand side. So it becomes 16t squared minus 160t plus 256 equals 0. Now, all of these are there's a greatest common factor of 16 between all of these, okay? So I can pull a 16 out. So this would be 16 times t squared minus 10t plus 16 equals 0. Now I want to try to factor this. two numbers that multiply together to give you positive 16 and to add to give you negative 10. That would be negative 8 and negative 2. So 16 times t minus 2 times t minus 8 equals 0. That would give me a time of 2 seconds and a time of 8 seconds. So on the way up at 2 seconds, it's on its way up to 256 feet, because at 5 seconds it's at its highest, and then at 8 seconds, it's back down to the 256 feet. Okay, so on the way up, okay, that's the first thing we're going to answer. We're going to find the velocity at 2 seconds. Okay, so that'd be 160 minus 32 times 2. So that would give you 96 feet per second. Okay, so now the speed. Well, the speed at 2 seconds would be equal to the absolute value of v of 2, and that's how you need to write it, okay? And then that would equal, well, what's the absolute value of 96? Well, it's just 96 feet per second. Okay, so then we need to do on the way down. So on the way down, that would be v of 8, and that'd be 160 minus 32 times 8. That would actually give you negative 96 feet per second. And then the speed on the way down would equal the absolute value of v of 8, which would wind up being just plain old 96 feet per second. Okay, so that's the velocity and the speed on the way up and also on the way down when the rock is at 256 feet above the ground. All right, last couple of things. So last question is this: what is the acceleration of the rock at any time t during its flight? Okay, so we know that s of t is equal to 160 t minus 16t squared. And we know s prime of t, which is also v of t, is equal to 160 minus 32t. So then s double prime of t, which is equal to v prime of t, which is equal to a of t, right? This would be the acceleration, okay? That would be, okay, so the derivative of 160 is 0, and so it would just be negative 32, okay? And because it's measured, the velocity is measured in feet per second, this is feet per second, or feet per second squared, okay? Or, like I said, you could do feet per second, okay? And finally, the last question actually really isn't even a calculus problem, okay? When does the rock hit the ground? Well, we know it hits the ground when the height is 0, okay? So s of t would have to equal 0. Well, s of t is the 160t minus 16t squared, so that we would just have to take set that equal to 0, and that would equal 160t minus 16t squared. There's a common factor here of 16t, and then that would be 0 is equal to 16t times 10 minus t. And so that would give you a time of 0, because 16 times 0 would be 0, okay? And this t right here would have to be 10. So t is equal to 10. Okay, so it hit the ground at 0 seconds. Well, no, it didn't hit the ground at 0 seconds. That's when it actually left. That's when it was on the ground at 0 seconds. And then 10 seconds later, it was back on the ground, okay? So the rock hit the ground. After 10 seconds, okay? And that is it for today. I know this was a very long lesson. This might be the longest lesson of the year, okay? And I know that. So I'm gonna stop talking and let you be done with this. Okay. Have a good day, everybody. See ya.